Hi, my name is Ron Lynch. I do web handling training and consulting. If you have seen any of my presentations before, you know that I like to squeeze everything I can out of the simple mathematics of web handling. I am not a hardcore mathematician, and I fall flat if I get a little past high school algebra. So no fourth order differential equations here. But the simple stuff gets you a long way to understand, explain, and solve the problems we see every day. Today we're going to tackle Camber. Camber is a web property that all of you have to deal with at one time or another. Measuring the radius of curvature and calculating the critical strain and tension are well-known procedures to avoid loose edges. Unmanageable laminate curl, mistracking, and cross-direction process variation can all be caused by Camber. This presentation covers Camber basics and some of the signs and symptoms that may indicate a Camber-related problem. A cambered web is, as the picture shows, a curved web. A common cause of camber is a web thickness profile across its width. When thousands of layers are wound onto a parent roll, the thicker side builds up a larger diameter and circumference than the thinner side. A viscoelastic material remembers it was stretched more around the thick side and retains the additional length when it is unwound. This creates the curve. When we think about cambered web, we normally only think loose edge and critical tension, but there is more to it than that. The amount of camber in a web is measured by its radius of curvature, rho. This can be measured by laying out a length of web, flattening it as naturally as possible, and measuring the bow height in the center of the length. From this, the radius of curvature can be calculated. The straighter the web, the larger the radius. So let's look at some of the problems. The long edge of a cambered web can be loose and floppy if insufficient tension is applied to the web. When we straighten a cambered web at zero tension, the long edge is rippled and wavy. In a machine, when a small amount of tension is applied, the short edge of the web will be stretched. The resulting stress profile will taper from a high value at the short edge to zero somewhere in mid-web. Beyond that, the long edge will still be at zero stress and loose. Tension is required to apply enough strain to pull the web straight and pull looseness from the long edge. As we apply more tension, the short edge stretches more and the stress profile extends farther across the web. At high enough tension, the stress profile will eventually reach the long edge. At this point, we know something. We have stretched the short edge to be as long as the long edge. Knowing this, we can calculate the strain on the short edge. Its strain equals the width divided by the radius of curvature. The wider the web and the shorter the radius, that is, the more it is curved, the greater will be the strain on the short edge. Our nice camber produces a nicely tapered strain profile, and the average strain on the web is 1/2 the strain on the short edge. This is called the critical strain. Multiplying the critical strain by web modulus, E sub W, gives the critical tension. Width and radius should be in the same units, and whatever units are used for modulus will be the same for tension. So again, as camber and web width increase, more tension is needed to straighten the web and pull out the looseness. When a web with a loose edge enters a nip, the extra length of the loose edge can accumulate in front of the nip until it is drawn into the nip, forming a cross-direction wrinkle. The critical strain and tension can also be estimated if you know the diameter difference across the parent roll. As a side note, for any lumpy bumpy parent roll, the lane-to-lane strain difference experienced by the web between the largest and smallest diameters is the diameter difference divided by the smaller diameter. You can't calculate the tension required to pull the looseness out, but this helps you understand if any damage will be done to your web by the strain. Cambered web tracks to the long edge under some conditions. The factors are the amount of camber, the tension, and the coefficient of friction with rollers. Experiments and models were done at Oklahoma State University that confirmed this, but the amount of mistracking their experiments found was small compared to what I expected. I suspect an unstudied factor is partial traction caused by air entrainment under the loose edge of the web. The Knox-Sweeney equation calculates the initial air film thickness between a web and roller when the web first contacts the roller. When the air film thickness exceeds a value determined by the properties of the system, the web will float above the surface of the roller. That is, no contact, no friction, no driving force. The incoming web stress is in the denominator of the equation. This means that the loose side of the cambered web will have a thicker air film and can lose traction before the tight side. With only a portion of the web in traction with the roller, this creates an irregular stress profile across the width of the web, and this is a common cause of both tracking variation and wrinkles. I come from a narrow web background, and I've seen webs run very nicely when in full traction with a roller, run very nicely when in full sliding with a roller, and I've also seen webs become very erratic on a few rollers mid-path for no obvious reason. I suspect this is due to partial and intermittent traction on those rollers. I'd like to see any research or hear any stories on this topic. Equal strain lamination is the objective of most lamination processes. Unequal strain laminates curl towards the ply with the higher strain. Cambered webs can never be combined at equal strain because the strain varies across their width. When laminated with matching average strain webs, the high strain side of the cambered web will curl one way and the low strain side will curl the other. The more the camber and the wider the web, the more the curl. One client, after designing and building a new meter-wide machine, found they had to cut their width to about 1/3 to avoid unacceptable curl after slitting the laminate into narrow strips. Another client tried to slit and retension the slit lanes before lamination, only to find the long edge accumulated and eventually found the floor. In both cases, camber was not considered when the machines and processes were designed, and their only option was to work with their supplier and hope to get a straighter web. Some products declare a product length on the package, and pesky government consumer protection agencies expect some statistical certainty that the declared length will be achieved. This usually means targeting to a longer length based on the standard deviation of the product length. If you have a wide front machine making narrower slit products, Camber alone makes products on the long side LW over rho longer than products from the short side. All else being perfect, you are giving away W over 2 rho times 100% of your web, trying to make the short side achieve the minimum length. If you random sample products and calculate the standard deviation without regard to lane, you are picking up not only the machine direction variation, which does cause product length variation of the short lane, but also the camber-induced cross-direction variation, which does not cause product length variation in any lane. The camber-induced variation adds to the standard deviation and raises the target above what would normally be required. This results in web giveaway and costs you money. The contact pressure between a web and radius surface is web stress divided by the radius. Because of the cambered web's tapered stress profile, the pressure between the web and radius will also taper across the width of the surface. Some processes use the pressure to set a bond between plies. Others use pressure against a surface to control fluid transfer. Continuous web folding depends on tension to force the web to conform to the folding bars. Any process that depends on tension or web pressure against a surface will see camber as a source of variation. The last problem experienced here is web breaks. The stress on the short edge of the web is higher than the average. This can be a source of web breaks. When thinking about running stress and tensile strength, factor in added edge stress due to camber. There is more to camber than just critical tension, and there are probably a few more problems I haven't seen or heard of. I hope you see something here that helps you avoid or solve a problem. My contact information is shown here. Feel free to contact me with any questions about this presentation or any other web handling questions. Thank you.